Space tears itself apart faster than the laws of physics predict. Two teams point telescopes at the same cosmos and arrive at incompatible truths. One measures expansion at 73 kilometers per second for every 3.26 million light-years of distance. The other calculates 67. This 6-unit gap represents a fundamental crisis in our understanding of reality itself. The ancient light from when the universe was 380,000 years old tells one story. Light from nearby galaxies tells another. Both measurements have been verified, cross-checked, and confirmed by independent teams using entirely different methods. The James Webb Space Telescope recently entered this debate with its unprecedented vision, and, rather than resolving the conflict, it amplified the discrepancy. The measurements are correct. The universe genuinely expands at two different speeds, depending on which epoch we examine. Consider two clocks in the same room displaying different times. One reads 3 o'clock, the other 3 to 10. Both function perfectly. Both measure the same flow of temporal passage. Yet they disagree. That paradox defines our current cosmological predicament. The gap has widened over the past decade. Initially, researchers hoped subtle measurement flaws would explain the divergence. Perhaps telescopes harbored hidden imperfections. Perhaps mathematical models contained unexamined assumptions. But every refined instrument, every careful recalculation, every meticulous analysis only deepened the split. When cosmologists observed the cosmic microwave background, they witnessed the universe as an infant. Photons from that primordial era have traveled nearly 14 billion years to reach our instruments. Scientists measure patterns of temperature fluctuations, feed that data into sophisticated models, and predict how rapidly space should stretch today. These predictions assume dark energy activated approximately 5 billion years ago, and has pushed space apart at a steady rate ever since. Local measurements suggest the universe expands 8% faster than those predictions allow. 8% across billions of years means something occurred that our models cannot accommodate. Perhaps dark energy possesses greater strength than calculations indicated. Perhaps it ignited earlier. Perhaps it has been changing over time, rather than remaining constant, as cosmologists assumed. The Planck satellite delivered humanity's most detailed portrait of the infant cosmos, confirming that space was once dense, scorching, and remarkably uniform. Using established physical laws, cosmologists evolved that early universe forward through time. They calculated how matter should aggregate into galaxies. They predicted how dark energy should accelerate expansion. Everything cohered beautifully into a coherent narrative from the Big Bang to the present epoch. Then astronomers measured the contemporary universe and discovered it running faster than the narrative predicts. Imagine observing childhood photographs of someone, then encountering them as an adult. The childhood images show a small, timid child. But the adult standing before you is tall, confident, and nothing like those early photos suggested they would become. Something transpired between then and now that altered the trajectory completely. That same disconnect spans 7 billion years of cosmic history. Early universe data indicates expansion should have accelerated gradually after dark energy emerged. Late universe data indicates it has been accelerating more vigorously. Both datasets are extraordinarily robust. Both have survived rigorous independent verification. Yet they narrate incompatible stories about the same stretch of temporal evolution. Scientists have searched for errors for over a decade. They have scrutinized telescope optics, questioned statistical methodologies, and re-examined every underlying assumption. The answer persists unchanged. The measurements are accurate. The universe genuinely appears to be expanding faster than physics predicts it should. Scientists rarely deploy the word crisis lightly, yet that is precisely the term now being invoked. In January 2025, a prominent astronomer stood before the American Astronomical Society and declared that what had been called the Hubble tension could no longer be characterized as mere tension. It had escalated into a full crisis. The measurements had achieved a level of precision where dismissing the problem became intellectually untenable. The term Hubble tension describes this collision between observation and prediction. Tension implies discomfort, something that might resolve itself naturally. Crisis suggests something broken, something demanding we fundamentally reconsider our assumptions. That shift in terminology marks a turning point in cosmological thinking. The expansion rate of the universe, designated the Hubble constant, ranks among the 6 most crucial numbers in cosmology. It determines the age of the cosmos. It influences calculations about dark matter distribution. It affects our understanding of galaxy formation and evolution. An incorrect value for this number means an incorrect cosmic narrative. For years, scientists measured this value at approximately 73 using nearby galaxies and supernovae. Other scientists measured it at approximately 67 using ancient photons from the early universe. A 6-unit discrepancy might sound trivial, but it represents roughly 8% divergence. In cosmic terms, that chasm is immense. That difference separates a universe 13.8 billion years old from one 12.8 billion years old. It separates models that function from models that collapse. Multiple independent research teams using entirely different methodologies all confirm the same division. Hubble Space Telescope measurements yield 73, Planck satellite measurements yield 67. James Webb Space Telescope observations confirmed Hubble's findings. Gravitational lensing studies produce intermediate values. Type Ia supernova observations lean toward the higher number. Red giant star measurements trend slightly lower. Every team conducts meticulous work. Every team validates their procedures. Every team arrives at genuine results. Yet those results refuse to harmonize. It resembles 5 credible witnesses describing the same accident. All 5 possess clear vision. All 5 observed carefully. Yet 3 describe a red vehicle and 2 describe a blue vehicle. Someone must be mistaken. But the evidence suggests everyone is correct. That impossibility defines the crisis. The scientific community spent the past decade hunting for measurement technique flaws. They wondered whether interstellar dust distorted the light. They questioned whether different stellar types behaved consistently across cosmic time. They re-examined every instrument and every calculation. Nothing explained the gap. A recent team published results using an innovative approach. They measured the distance to a massive cluster of galaxies relatively close to Earth with unprecedented precision. They used that measurement as the foundation of the cosmic distance ladder. The result emerged at 76.5 kilometers per second per megaparsec, even higher than previous measurements. The tension just intensified. This compels physicists to declare a crisis. When improved measurements amplify rather than resolve the problem, something foundational must be incorrect. Either our instruments systematically deceive us in ways we cannot detect, or our theories about the universe remain incomplete. What if the force blamed for the universe's acceleration never existed? A researcher from New Zealand recently published findings challenging one of cosmology's bedrock assumptions. Dark energy, this research proposes, represents a misidentification. We have been mistaking the uneven flow of time across space for a mysterious, accelerating force. According to this analysis, dark energy becomes unnecessary. The Standard Model asserts dark energy constitutes 68% of universal content. It supposedly manifests as a constant anti-gravity force, pushing space apart with increasing vigor. We cannot observe it directly. We cannot detect it through any instrument. We only infer its existence because galaxies appear to rush away from us at an accelerating rate. Scientists invented dark energy to explain that acceleration. The timescape model offers an alternative explanation. Research teams analyzed light from distant supernova explosions using improved techniques. They discovered the universe does not expand uniformly as assumed. Instead, it exhibits profound lumpiness. Space stretches faster in vast empty regions called cosmic voids, and slower in dense regions packed with galaxies. When you average these different expansion rates without accounting for how genuinely lumpy the universe actually is, you generate a false impression of acceleration. General relativity provides the key insight enabling this interpretation. Gravity does not merely bend space. It also warps time itself. Clocks tick slower in powerful gravitational fields. A clock on Earth runs marginally slower than a clock in empty space. Scale that effect to cosmic distances and time flows differently depending on your location in the universe. Inside a galaxy cluster where gravity is intense, time runs slower. In a cosmic void where almost no matter exists, time runs faster. The difference appears small, but across billions of years, it accumulates significantly. A clock in a void would measure billions of years more elapsed time than a clock in a galaxy cluster, even though both started ticking at the Big Bang. When we observe distant galaxies, we peer backward through time. The light has been traveling for billions of years, but that light passed through regions where time flows at different rates. The stretching we observe is not necessarily acceleration. It might simply result from light traveling through this lumpy, time-warped universe. Consider driving on a highway where speed limits change. In some sections, you travel 50 miles per hour. In others, 70. If someone measured only your average speed without knowing about the varying limits, they might think you were accelerating when you were simply following different rules in different zones. This model has been tested against supernova data, and in some analyses it fits better than the standard model. Research teams used data from over 1,000 supernovae and discovered that accounting for the universe's lumpiness removed the need for dark energy entirely. The apparent acceleration becomes an artifact of how we calibrate time and distance. This challenges 27 years of consensus. In 1998, two teams discovered that the universe's expansion was accelerating. They received the Nobel Prize in 2011 for that discovery. Dark energy became the centerpiece of modern cosmology. Now, some scientists argue we invented a placeholder for something we did not understand. For a century, cosmologists assumed space was smooth like blended soup, but reality looks nothing like that idealization. The equations describing cosmic expansion date back to 1922, when a physicist developed them based on Einstein's general relativity. These equations assume the universe is homogeneous and isotropic, meaning it looks identical in all directions and at all locations once you zoom out sufficiently. Treat the universe like a featureless fluid. Average everything, and the mathematics becomes manageable. That assumption worked beautifully for decades. But zoom in from those cosmic scales, and you observe something completely different. Galaxies are not scattered randomly like grains of sand. They cluster into groups. Groups cluster into superclusters. Superclusters form sheets and filaments that wrap around enormous voids. The universe resembles a sponge with dense regions separated by empty bubbles millions of light years across. This structure is called the cosmic web, confirmed by decades of observation. Empty voids and dense clusters do not expand identically. Voids filled mostly with dark energy and minimal matter expand faster. Dense regions where gravity from visible and dark matter dominates expand slower or even contract locally as galaxies pull together. The smooth universe equations cannot handle this complexity. They assume you can blur all details and treat the universe as uniform. But if different regions expand at genuinely different rates, averaging them together produces incorrect results. Imagine attempting to describe ocean waves by averaging water height across the entire Pacific. You would obtain a number, certainly, but that number would communicate nothing useful about actual waves surging and falling. The universe might resemble those waves more than a calm, uniform sea. Scientists have known about the cosmic web for decades, but assumed it did not matter for expansion calculations. The reasoning was that on sufficiently large scales, the lumpiness averages out, and smooth universe equations work adequately. Recent research suggests that assumption is incorrect. The timescape model accounts for lumpiness directly. It tracks how different regions expand at different rates and how time flows differently in those regions. When you perform that mathematics, the apparent acceleration vanishes. What we interpreted as dark energy speeding up expansion is actually just the uneven, lumpy expansion of a structured universe. This is not settled science yet. The standard model still fits most observations well, but the timescape model fits some datasets even better, and it accomplishes this without invoking mysterious, invisible energy. The European Space Agency launched a satellite in 2023 specifically to test these ideas. That satellite is mapping the cosmic web in unprecedented detail, measuring how galaxies cluster and how voids expand. Data from this mission should reveal whether lumpiness matters enough to eliminate the need for dark energy. Results are beginning to arrive now. A telescope launching in 2027 will add even more precision. These missions could settle the debate within a few years. Either dark energy is real, and we need to determine its nature, or it is an illusion created by treating a lumpy universe as smooth. Both possibilities rewrite cosmology, just in different ways. A clock in empty space measures billions of years more than a clock inside a galaxy cluster. That changes everything. Einstein's general relativity revealed something profoundly strange about time. It does not flow at a constant rate everywhere. Gravity warps time. The stronger the gravitational field, the slower time passes. This has been confirmed in terrestrial experiments. Atomic clocks at sea level tick marginally slower than atomic clocks on mountaintops because they sit deeper in Earth's gravitational well. Scale that effect to the universe, and it becomes profound. Inside a galaxy cluster, where trillions of stellar masses pull on space, time runs slower than in the vast voids between clusters. The difference is minuscule from moment to moment, but across 13.8 billion years, it accumulates into billions of years of difference. A clock that started ticking at the Big Bang and remained in a void would now read significantly more elapsed time than a clock that spent those eons inside a dense galaxy cluster. This is confirmed physics, not speculation. Time dilation is a direct consequence of general relativity. We measure the universe's expansion by observing light from distant galaxies. That light has been traveling for billions of years, passing through voids and clusters. But light does not experience time. It travels at constant speed regardless of local time dilation. When we analyze that light to determine how much the universe has expanded, we use clocks that ran at different rates depending on where the light traveled. Consider measuring the growth of a tree using photographs taken with cameras that had different shutter speeds. Some photographs captured time normally, others captured it in slow motion. If you do not account for the different shutter speeds, you will misjudge how fast the tree actually grew. The timescape model takes time dilation seriously. It does not treat the universe as a uniform blob where time flows identically everywhere. Instead, it tracks how time flows differently in voids versus clusters. When you account for these variations, the expansion history looks different. What appeared to be acceleration might just be our misunderstanding of how to compare clocks across cosmic distances. In a void, where almost no matter exists, time runs faster. The expansion of space also happens faster because there is less gravity to slow it down. In a cluster, gravity is intense, time runs slower, and expansion is suppressed. We live in a moderately dense region, somewhere between these extremes, and we are attempting to make sense of light that traveled through all of them. The mathematics becomes complicated rapidly, but the core concept is simple. If time does not flow uniformly, then using a single cosmic clock to describe expansion is incorrect. You need different clocks for different regions, and you need to account for how those clocks relate to each other. Research teams calculated what the universe's expansion should look like when you properly account for time dilation across voids and clusters. The result matches observations without requiring dark energy. The apparent acceleration is real in the sense that we genuinely observe it, but it is not caused by a mysterious force. It is caused by comparing measurements made with clocks that were not synchronized. This remains under testing. The predictions differ slightly from standard models in ways that future observations should be able to confirm or rule out. Upcoming telescopes will map enough of the cosmic web to test whether time dilation in voids matters as much as the model suggests. If the model holds up, dark energy was the wrong explanation for 27 years. What we see when we look at the universe might be fundamentally misleading. Light takes time to travel. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. That galaxy looks distant because its light has been stretched by the expansion of space during its journey to us. The amount of stretching tells us how much the universe expanded during that time. At least that is what we thought. But if time flows at different rates across the cosmic web, then light traveling through voids experiences less time passage than light traveling through clusters. The stretching we measure depends on how long the light traveled. But measuring that duration requires knowing which clock to use, a void clock or a cluster clock. Standard cosmology uses a single universal time. It assumes we can discuss the age of the universe as if there is one cosmic clock ticking uniformly everywhere. That makes calculations simple, but it might be incorrect. If different regions genuinely experience different amounts of time since the Big Bang, then the concept of a single cosmic age breaks down. The timescape model describes this with a concept called kinetic energy of expansion. In simple terms, different parts of space are expanding with different amounts of energy. Voids expand vigorously. Clusters expand slowly or not at all. When you attempt to average these different expansion rates to obtain a single number for the Hubble constant, you create an illusion. Consider averaging the temperature of a room that has a fireplace at one end and an open window at the other. You might calculate an average of 70 degrees, but no part of the room actually is 70 degrees. Near the fireplace, it is 90. Near the window, it is 50. The average is real mathematically, but meaningless physically. That might be happening with cosmic expansion. We calculate an average expansion rate, interpret it as acceleration caused by dark energy, but the average is misleading. The universe is not accelerating uniformly. It is expanding unevenly in a complex pattern we have been mistaking for something simpler. Light from distant supernovae travels through this lumpy structure. Some light paths cross more voids, some cross more clusters. The stretching we measure depends on the specific path each light beam took. When we assume all paths are equivalent because space is uniform, we introduce errors that look like acceleration when they might just be path differences. This is incredibly difficult to test because we cannot replay cosmic history with different assumptions and see which matches reality better. We only get one universe to observe, but we can test the models against different datasets and see which makes better predictions. So far, the timescape model performs well when tested against supernova data. It predicts the brightness and distance relationships we observe without needing dark energy. The standard model also fits the data, but requires invoking an invisible force that comprises more than 2/3 of the universe's energy budget. The simplest explanation should be chosen when both fit the evidence, but here, simplicity is debatable. The timescape model eliminates dark energy, which sounds simpler, but it requires tracking time dilation and varying expansion rates across cosmic structure, which sounds more complex. The true test will come from mapping the cosmic web precisely enough to measure whether voids really do expand faster in the way the model predicts. We are close to having that data. Within a decade, we will know whether the cosmic web is playing tricks on our measurements. The force we thought was constant might have been evolving all along. An instrument known as the Dark Energy Spectroscopic Instrument spent years mapping millions of galaxies. The project aimed to measure how dark energy has affected the universe over the past 11 billion years. In 2024, the team released their first results, and they contained a surprise that has physicists rethinking everything. Dark energy appears to be changing over time. This is preliminary, not yet confirmed beyond doubt, but the evidence is strong enough to take seriously. The standard model treats dark energy as a cosmological constant, a property of space itself that never varies. Empty space has fixed energy density, and that energy pushes space apart at a steady rate. This assumption made calculations elegant and matched observations reasonably well for 2 decades. The new data suggests something different. When the team analyzed how galaxies cluster at different cosmic ages, they found hints that dark energy was stronger in the distant past than it is today. The effect is subtle, but if confirmed, it means dark energy is dynamic, not constant. Think of wind speed. You might measure wind blowing at 10 miles per hour and assume it is constant. But if you check historical records, you might find it used to blow at 15 miles per hour and has been gradually slowing down. That changes how you predict future conditions entirely. If dark energy is weakening, the universe's expansion might be slowing down rather than speeding up. That flips the story we have been telling. For 27 years, we thought the universe was accelerating faster and faster toward an eventual heat death where everything becomes cold, dark, and infinitely separated. But if dark energy is fading, acceleration might stop. The expansion might even reverse. The implications are staggering. A reversing expansion leads to a big crunch where the universe collapses back on itself. Galaxies would rush together instead of apart. Space would shrink instead of stretch. Everything that expanded since the Big Bang would contract back to a point. The measurement was achieved by looking at baryon acoustic oscillations, a characteristic distance between galaxies that acts like a cosmic ruler. By measuring how this distance has changed over billions of years, they reconstructed the expansion history. The pattern they found does not match a constant cosmological constant. It matches varying dark energy better. This could explain the Hubble tension. If dark energy behaved differently in the past than it does now, then predictions based on the early universe would naturally disagree with measurements of the current universe. The mismatch would not be an error. It would be evidence that dark energy evolved. But other measurements do not show the same variation. Planck satellite data fits constant dark energy well. Supernova observations are consistent with constant acceleration. The hint of change is statistically significant, but not overwhelming. It could be a real signal or a statistical fluke that will disappear with more data. The team is continuing observations. By 2027, they will have enough data to confirm or rule out evolving dark energy with much higher confidence. Other missions will add independent measurements. Within a few years, we will know whether dark energy is truly changing or whether they saw noise in the data. If it is changing, the next question becomes why? What physical process would cause the energy density of empty space to vary over time? We do not have good theories for that. It would require new physics beyond the standard model. New research suggests expansion might have already begun to decelerate. A team from South Korea led an analysis of decades of supernova data with a fresh approach. Their findings, published recently, claim the universe has already entered a phase of slowed expansion. If true, this marks one of the most important discoveries in cosmology since the detection of acceleration itself. Standard thinking says dark energy started dominating about 5 billion years ago and has been accelerating expansion ever since. The acceleration should continue indefinitely, eventually ripping apart galaxies, solar systems, and even atoms in a scenario called the Big Rip. Or expansion should continue forever at an accelerating rate, leading to heat death where the universe becomes cold, dark, and empty. This analysis suggests that is wrong. According to their calculations, expansion already peaked and is now slowing down. We are past the maximum acceleration phase and entering deceleration. Dark energy, if it exists, is losing its battle against gravity. Gravity tries to pull matter together, slowing expansion. Dark energy pushes space apart, speeding expansion. For most of cosmic history, gravity dominated, slowing the expansion that started with the Big Bang. Then dark energy took over, and expansion accelerated. Now, according to this research, dark energy is weakening, and gravity is winning again. Think of throwing a ball upward. Gravity slows the ball until it stops and falls back down. The universe's expansion might follow a similar pattern. It exploded outward, slowed down, temporarily accelerated when dark energy kicked in, but is now slowing again as dark energy fades. If this continues, expansion could stop entirely, then reverse. Galaxies would start moving toward each other instead of away. Space itself would contract. Over hundreds of billions of years, the universe would collapse back into a big crunch, the opposite of the Big Bang. This ties into the findings about evolving dark energy. If dark energy is getting weaker over time, then deceleration is exactly what we would expect to see. The universe accelerated when dark energy was strong. Now that it is weakening, acceleration is giving way to deceleration. But other scientists remain skeptical. The evidence for deceleration is not overwhelming yet. The measurements are subtle and depend on how you interpret complex data. Different analysis methods give different results. Some show continued acceleration. Others show slowing. The uncertainty is still too large to declare victory for either side. What makes this so important is the fate of everything. If acceleration continues, the universe ends in cold isolation. If deceleration continues, the universe ends in a fiery collapse. These are not just abstract possibilities. They are actual futures awaiting all matter, energy, and structure in existence. Upcoming telescopes will help settle this debate. They will measure the expansion rate at different cosmic ages with unprecedented precision. If expansion really is slowing, these instruments will detect it clearly. If it is still accelerating, the data will show that too. We are living at a unique moment in cosmic history. For the first time, we have instruments powerful enough to measure whether the universe's fate is isolation or collapse. The answer could come within the next 5 years. Until then, both futures remain possible. If expansion reverses, everything that exists will be crushed back into a single point. Imagine watching a film of the universe's history in reverse. Galaxies rush together instead of apart. Stars collide and merge. Gas clouds compress and heat up. Space itself shrinks, forcing everything closer and closer together. That is the Big Crunch, the mirror image of the Big Bang. This is a theoretical possibility, not a confirmed prediction, but recent findings make it worth considering seriously. For decades, cosmologists assumed the universe would expand forever. Matter spreads out. Stars burn out. Black holes evaporate. Everything fades to cold darkness. That future seemed certain after the discovery of accelerating expansion in 1998. Dark energy appeared unstoppable, destined to push everything apart for eternity. But if dark energy is weakening, that future changes. Gravity never stops pulling. Once dark energy fades enough, gravity takes over and reverses the expansion. The universe would contract slowly at first, then faster and faster as matter drew closer together and gravitational pulls strengthened. Over hundreds of billions of years, distant galaxies would stop receding and start approaching. The redshift we currently observe, where light from galaxies stretches toward red wavelengths because they are moving away, would reverse to blue shift as they move toward us. The night sky would gradually brighten as galaxies crowded together. Eventually, galaxy clusters would collide. Stars would pass near each other, disrupting planetary orbits. Some worlds would be flung into interstellar space. Others would spiral into their stars. The organized structure of galaxies would break down into chaos. As contraction continued, gas clouds between galaxies would compress and heat up. The universe would get hotter instead of cooler. Background radiation would shift from the cold microwave frequencies we measure today toward infrared, then visible light, then ultraviolet, then X-rays. Space itself would become an oven. Stars would merge into larger, hotter objects. Planets would vaporize. Matter would break down into plasma as temperatures soared. Eventually, even atoms would be torn apart by the extreme energy. The universe would return to conditions like those moments after the Big Bang, but in reverse. Finally, all matter, energy, and space would converge into a single point of infinite density. Time itself would end along with everything else. That is the Big Crunch. This scenario depends on dark energy continuing to weaken or disappearing entirely. If dark energy remains even slightly positive, expansion continues forever, and the Big Crunch never happens. The current evidence for weakening dark energy is intriguing, but not definitive. We need more data. Some physicists find the Big Crunch appealing because it suggests the universe might be cyclic. A Big Crunch could trigger another Big Bang, restarting cosmic expansion with fresh conditions. The universe might go through endless cycles of expansion and contraction, each cycle lasting hundreds of billions of years. Other physicists think the Big Crunch is unlikely, because measurements still favor continued expansion, just at a slowing rate. The universe might coast to a stop asymptotically, never quite reversing, but never expanding much further either. The only way to know is to keep measuring. Track the expansion rate over the next decade. Watch how it changes. See if deceleration continues or if acceleration reasserts itself. The answer will tell us the ultimate fate of everything that exists. And that answer is coming soon. Before the dark energy we know, there might have been another force that appeared for an instant and vanished forever. Physicists recently proposed something radical. What if dark energy existed twice in cosmic history? Once in the universe's first moments, then again billions of years later. The early version appeared for a fraction of a second, affected the infant cosmos, and disappeared completely. The late version is what we observe today, driving current acceleration. This is speculative theory meant to solve multiple problems at once. The theory addresses two major mysteries. First, the Hubble tension where measurements do not match predictions. Second, the unexpected abundance of bright galaxies seen by James Webb Space Telescope in the very early universe. Standard models predict far fewer, large, bright galaxies should have formed so quickly after the Big Bang, yet Webb keeps finding them. Early dark energy would solve both problems if it existed. Imagine a force that turned on when the universe was incredibly young, perhaps when it was less than a few 100,000 years old. This force would be similar to dark energy, but temporary. It would push space apart briefly, accelerating expansion during a crucial period. Then, it would shut off completely, leaving no trace except its effects on the universe's structure. This burst of acceleration would change how matter clumped together in the early cosmos. It would allow density fluctuations to grow faster, seeding the formation of galaxies earlier than standard models predict. More early galaxies means more bright galaxies visible to Webb, matching what we actually observe. Early dark energy would also affect the expansion rate in a way that resolves the Hubble tension. If the universe expanded faster than usual for a brief early period, then predictions based on the cosmic microwave background would need adjustment. The adjustment would bring those predictions closer to the higher local measurements we observe today. Think of a vehicle that briefly shifts into a higher gear during part of the journey. If you only measure average speed at the beginning and end, you will misjudge the total travel time unless you account for that gear shift. Early dark energy would be cosmic history's gear shift. The challenge is explaining where this early dark energy came from and why it disappeared. Dark energy today appears to be a property of space itself, something that does not decay or change much over time. Early dark energy would need to be something different, perhaps a field that only existed under extreme conditions present in the infant universe. Some theories propose a scalar field similar to the field thought to drive cosmic inflation, but distinct from it. This field would have high energy when the universe was young and dense. As space expanded and cooled, the field would roll down to lower energy states, eventually vanishing entirely. The mathematics works in principle, but there is no direct evidence yet. The theory makes predictions that future observations should be able to test. Detailed measurements of the cosmic microwave background might reveal subtle imprints left by early dark energy. Continued observations of early galaxies will either support or contradict the prediction of enhanced early structure formation. If early dark energy existed, it would add a new chapter to cosmic history. The universe would have experienced three distinct phases of expansion. First, inflation, the exponential burst right after the Big Bang. Second, early dark energy, a temporary acceleration during the first 100,000 years. Third, late dark energy, the current acceleration that started billions of years ago. Each phase would have shaped the cosmos differently, leaving its signature in the structure we observe today. Light from opposite sides of the universe looks identical, but those regions should never have communicated. When scientists mapped the cosmic microwave background, they found something remarkable. The temperature is nearly uniform across the entire sky. Whether you point your telescope north, south, east, or west, you measure almost exactly 2.7 Kelvin everywhere. Tiny variations exist, but they are less than 1 part in 100,000. The universe looks extraordinarily smooth. Here is why that is bizarre. Light has a speed limit. Nothing, not even information, can travel faster than light. Since the Big Bang happened 13.8 billion years ago, light has only had 13.8 billion years to travel. That means any given region of space can only have communicated with other regions within 13.8 billion light-years. That distance is called the cosmic horizon. When we look at opposite sides of the sky, we see regions separated by far more than that. Those regions are so distant that light from one could never have reached the other in the age of the universe. They are beyond each other's horizons. They are causally disconnected, yet somehow they have the same temperature. Consider two strangers on opposite sides of Earth who have never met, never communicated, and do not know the other exists. Yet they both choose to wear the exact same outfit on the same day. That is suspicious. Something must have coordinated them, even though they have never been in contact. The universe faces the same puzzle. How did opposite regions end up with identical temperatures if they could never exchange energy or information? What coordinated them? Standard Big Bang theory has no answer. If the universe simply expanded from a hot, dense state without any special early phase, then different regions should have different temperatures. There is no mechanism to make them uniform. The smoothness we observe should not exist. This is called the horizon problem, and it troubled cosmologists for decades. Cosmic inflation provides the solution. If the universe underwent a period of exponential expansion very early in its history, before the cosmic microwave background formed, then regions that are now separated were once much closer together. They were within each other's horizons back then. They had time to exchange energy and reach the same temperature. Then, inflation blew them apart. Space expanded so rapidly that regions which were once in contact got stretched to opposite sides of the observable universe. They look disconnected now, but they share a common history from before inflation. Imagine inflating a balloon. Draw two dots close together on the deflated balloon. As you inflate it, those dots move apart, eventually ending up on opposite sides. Someone looking at the inflated balloon might think the dots were never connected, but they were close together before the expansion. That is what inflation does to the universe. It takes a small, smooth patch of space where everything reached equilibrium, then expands it to cosmic size. The smoothness is real, but it is not mysterious. It is just the remnant of a time before inflation, when everything was in contact. Inflation solves the horizon problem elegantly. The universe is not smooth by accident. It is smooth because it started from a tiny region that had time to equilibrate before inflating to cosmic scale. But inflation itself raises new questions. The universe is flat to incredible precision, but the odds of that happening naturally are essentially zero. Space can have curvature just like surfaces in everyday life. A sphere is positively curved. A saddle is negatively curved. A plane is flat with zero curvature. General relativity says the universe's overall geometry depends on its density. Too much matter, and it curves into a sphere. Too little, and it curves into a saddle. Exactly the right amount, and it stays flat. The problem is that the right amount is incredibly specific. Even tiny deviations from that critical density early in cosmic history would have grown enormous over time. If the density was slightly too high, the universe would have collapsed back on itself billions of years ago. If slightly too low, it would have expanded so fast that no galaxies could ever form. Measurements show the universe is flat to better than 1% accuracy. That means the density is at or incredibly close to the critical value. For the density to be this close to critical now, it must have been absurdly close to critical in the early universe. We are talking about precision to 1 part in 10 to the 62nd power. Think of balancing a pencil on its tip. If the pencil is even slightly tilted at the start, it falls over immediately. For the pencil to still be balanced billions of years later, it must have started perfectly vertical to impossible precision. That is the flatness problem. Why would the universe start with exactly the right density? What mechanism fine-tuned it so precisely? Standard Big Bang theory offers no explanation. It is just an incredibly lucky initial condition that we have to assume without justification. Cosmic inflation solves this problem too. During inflation, space expanded by a factor of at least 10 to the 26th power. That is 1 followed by 26 zeros. Any curvature that existed before inflation got stretched flat by this enormous expansion. Imagine drawing a circle on a balloon, then inflating the balloon to the size of Earth. The circle would look flat because the curvature got diluted over such a vast area. You would need incredibly precise instruments to detect any remaining curvature. That is what inflation did to the universe. Any curvature that existed before inflation became undetectable after inflation. The universe appears flat today, not because it started with a miraculously special density, but because inflation stretched it flat regardless of how it started. This makes flatness generic rather than special. Any universe that undergoes inflation should look flat afterward. The fine-tuning problem disappears because inflation naturally drives the geometry toward flatness. But inflation creates its own fine-tuning problems. What triggered inflation? Why did it last long enough to solve the flatness and horizon problems, but not so long that it erased everything? What stopped inflation and allowed normal expansion to resume? These questions remain unanswered. Some physicists argue that inflation just trades one set of problems for another. Instead of explaining why the initial conditions were special, we now have to explain why inflation happened at all, and why it had the right properties to produce our universe. Others counter that inflation is a better explanation, because it is a dynamic process that evolves according to physical laws, rather than just asserting special initial conditions without justification. Inflation is testable in ways that initial conditions are not. The debate continues, but most cosmologists accept inflation as the best explanation we have for the universe's flatness. The alternative is accepting an absurdly unlikely coincidence. And coincidences like that beg for better explanations. Space expanded by a factor of 1 trillion in less than a trillionth of a second. Cosmic inflation is one of the most extreme events ever proposed in physics. In a time interval shorter than a blink, the universe grew from subatomic size to something cosmically vast. The expansion rate during inflation was so fast that space itself stretched faster than light speed. This does not violate relativity because space can expand at any rate. Only objects moving through space are limited to light speed. Before inflation, the observable universe was smaller than an atom. After inflation, it was larger than a grapefruit. That might not sound like much, but the expansion factor was approximately 10 to the 26th power. That is the number 1 followed by 26 zeros. For comparison, the expansion from the end of inflation to today has only been about 10 to the 3rd power, a factor of 1,000. Inflation crammed most of the universe's expansion into a tiny fraction of a second. Everything since has been coasting. What drove this exponential expansion? Physicists propose a field called the inflaton. Similar to other quantum fields but with unusual properties, the inflaton field had high energy in the early universe. That energy behaved like negative pressure, pushing space apart rather than pulling it together like normal matter. Think of a compressed spring. The spring has stored energy that wants to expand outward. The inflaton field was like that, except instead of pushing matter apart, it pushed space itself apart. And unlike a normal spring that weakens as it expands, the inflaton field maintained constant energy density even as space grew. More space meant more total energy, which drove even faster expansion. This is called exponential growth. Each moment, space doubles in size, then doubles again, then again. Doubling repeatedly leads to explosive growth. In about 100 doubling times, something grows by a factor of 10 to the 30th power. Inflation achieved this in a fraction of a second. Eventually, the inflaton field decayed. It transitioned from high energy to low energy, releasing its stored energy as ordinary matter and radiation. This process, called reheating, filled the universe with the particles that eventually formed atoms, stars, and galaxies. The exponential expansion stopped, and normal, slower expansion took over. Inflation explains more than just the horizon and flatness problems. It also explains where the tiny density variations came from that seeded galaxy formation. During inflation, quantum fluctuations in the inflaton field got stretched to cosmic size. These fluctuations created slightly denser and less dense regions in space. After inflation ended and matter formed, gravity pulled matter toward the denser regions. Over billions of years, those tiny variations grew into galaxies and galaxy clusters. The structure we see in the universe today traces back to quantum fluctuations during inflation. This is a remarkable connection. Quantum mechanics governs the behavior of subatomic particles. Cosmology governs the behavior of the entire universe. Inflation links them. The largest structures in existence originated from the smallest quantum jitters, magnified by inflation to astronomical scales. The theory makes predictions that can be tested. Inflation should have produced gravitational waves, ripples in spacetime itself, along with the density fluctuations. Detecting these primordial gravitational waves would confirm inflation directly. Several experiments are searching for them now. The first inflation model broke physics in a way that nearly killed the theory. When the concept was first proposed in 1981, the originator recognized a fatal flaw in his own idea. The model solved the horizon and flatness problems beautifully, but it failed to explain how inflation ended properly. The universe was supposed to transition from rapid inflation to normal expansion, converting the inflaton field's energy into particles. But the original mechanism did not work. The problem was reheating, or rather, the lack of it. The original model relied on something called bubble nucleation. The inflaton field existed in a high-energy state called false vacuum, like a ball balanced on a hilltop. Eventually, the field would tunnel through to a lower energy state called true vacuum, like the ball rolling down into a valley. This transition would release enormous energy, reheating the universe and creating matter. In the original picture, bubbles of true vacuum would form randomly in the sea of false vacuum. Each bubble would expand at light speed. When bubbles collided, they would release energy and create particles. The universe would heat up through these collisions. But here is what went wrong. If inflation lasted long enough to solve the horizon and flatness problems, the bubbles became incredibly rare. Space expanded so fast that bubble formation could not keep up. In any observable region, only one bubble would form, if any. There would be no collisions, no energy release, and no reheating. The universe would remain cold and empty forever. Think of raindrops forming in a storm, but the clouds expand faster than rain can form. The drops become so spread out that they never hit each other or the ground. You end up with a vast dry sky, despite the presence of moisture. The originator realized this problem immediately. He published his paper anyway, hoping someone would find a solution. The idea of inflation was too powerful to abandon over a technical difficulty. Within a year, others developed a fix. Instead of bubbles nucleating abruptly, they proposed that the inflaton field could roll slowly down from high energy to low energy, like a ball rolling gently down a hill rather than suddenly appearing at the bottom. This process, called slow roll inflation, avoided the bubble problem entirely. In slow roll inflation, the field does not transition through quantum tunneling. It just gradually decreases in energy as the field evolves according to its equations of motion. When the field reaches low enough energy, it oscillates rapidly and decays into particles. This happens smoothly throughout space, not just in localized bubbles. Reheating occurs everywhere simultaneously. This version of inflation works. It solves the original problems while also successfully reheating the universe. It has become the standard picture of how inflation operated. But the story illustrates something important about theoretical physics. Ideas often start flawed. The first version of a theory rarely works perfectly. Scientists identify problems, propose fixes, and gradually refine the idea until it matches observations. Inflation survived its initial failure because the core concept was valuable enough to deserve repair. Today, inflation theory continues evolving. Physicists have proposed dozens of different inflation models with different field properties and different predictions. Some involve multiple fields. Some have complex energy landscapes. Some connect to string theory or quantum gravity. No single inflation model has been proven correct yet. The data we have narrows the possibilities, but does not uniquely identify one mechanism. Future observations might finally pin down exactly how inflation worked. Until then, we know inflation happened, but the details remain mysterious. The seeds of every galaxy in existence began as random quantum jitters, smaller than an atom. Quantum mechanics tells us that nothing is ever truly still. Even in perfect vacuum, fields fluctuate randomly at microscopic scales. These fluctuations are tiny, lasting for infinitesimally short moments before disappearing. They are the universe's way of being uncertain at the smallest scales. Normally, these quantum jitters have no lasting effect on anything large. But during inflation, something extraordinary happened. As space expanded exponentially, quantum fluctuations in the inflaton field got stretched. A fluctuation that started smaller than a proton grew to the size of a galaxy, then a galaxy cluster, then even larger. The expansion happened so fast that the fluctuations did not have time to smooth out or disappear. They froze in place, becoming permanent features of the cosmic landscape. Consider taking a photograph of ripples on water. The ripples are temporary and would normally fade away, but if you freeze them in a picture, they become permanent. Inflation did something similar to quantum fluctuations, freezing them into the structure of space itself. These frozen fluctuations became density variations in the early universe. Some regions had slightly more energy than average, others had slightly less. The differences were tiny, about 1 part in 100,000, but they were enough. When inflation ended and matter formed, gravity amplified these tiny differences. Regions that were slightly denser had stronger gravity, pulling in more matter. Regions that were slightly less dense lost matter to their denser neighbors. Over millions and billions of years, these tiny seeds grew into the cosmic web we observe today. Every galaxy exists because of a quantum fluctuation during inflation. Every galaxy cluster, every supercluster, every void traces back to random quantum noise magnified to cosmic proportions. The universe's largest structures have the smallest possible origin. This is confirmed by observations. The cosmic microwave background shows the pattern of hot and cold spots that correspond exactly to these frozen quantum fluctuations. The statistical properties of those spots match what we would expect from quantum mechanics. The universe's structure follows quantum rules scaled up to astronomical size. Scientists can even calculate the exact spectrum of fluctuations inflation should produce. The power spectrum, as it is called, describes how much variation exists at different scales. Inflation predicts a nearly scale-invariant spectrum, meaning fluctuations have similar strength whether they are galaxy-sized or supercluster-sized. Observations confirm this prediction. The connection between quantum mechanics and cosmology is one of the most profound insights in physics. The smallest and largest scales of nature are not separate. They are linked through inflation. What happens at subatomic scales determines the structure of the entire observable universe. But this raises deep questions about randomness and determinism. If galaxy locations depend on random quantum fluctuations, then the universe's structure is fundamentally probabilistic. There is no deeper reason why galaxies formed where they did. It is just quantum chance, amplified and frozen. Some physicists find this troubling. Others find it beautiful. The universe's grandest structures emerge from pure randomness, given form by the laws of physics acting over cosmic time. Either way, every star you see exists because of quantum uncertainty. The cosmic microwave background has strange patterns in its temperature that should not be there. When scientists analyze the cosmic microwave background, they break it down into components called multipoles. These describe temperature variations at different angular scales across the sky. Low multipoles represent large-scale patterns. High multipoles represent small-scale patterns. The Standard Model predicts how strong each multipole should be based on inflation and cosmic evolution. Most multipoles match predictions perfectly, but some do not. The Quadrupole, which describes the largest scale temperature pattern, is unexpectedly weak. The Octupole, the next scale up, shows strange alignment with the plane of our solar system. This alignment makes no sense. The cosmic microwave background formed billions of years before our solar system existed. There should be no relationship between them. These are confirmed anomalies, not measurement errors, though their statistical significance remains debated. The quadrupole problem means the universe has less large-scale temperature variation than expected. Think of measuring sound waves and finding that the deepest bass notes are quieter than they should be. The physics that generated all the other frequencies should have generated strong bass too, but it did not. Several explanations have been proposed. Maybe inflation lasted slightly longer than the Standard Model assumes, erasing some large-scale fluctuations. Maybe the universe has some large-scale structure beyond what we can observe, affecting how we perceive patterns within our observable patch. Maybe there is new physics that suppresses fluctuations at large scales. The alignment with our solar system's plane is even stranger. The octupole and quadrupole both show preferential orientation toward the plane of our solar system. This was first noticed in the early 1990s, then confirmed by subsequent missions. It has been nicknamed the axis of evil because it seems to violate the cosmological principle that the universe should look the same in all directions. Some scientists think this is just statistical fluke. When you analyze complex data, occasionally you find patterns that look meaningful, but are actually random. The human brain is very good at seeing patterns, even in noise. Maybe we are over-interpreting random alignments. Others think it is real evidence for something beyond the Standard Model. Maybe the universe has some preferred direction. Maybe our observable patch sits inside a larger structure with its own orientation. Maybe the cosmological principle is wrong, and the universe is not truly isotropic. Loop quantum cosmology offers one explanation. This theory, which applies quantum mechanics to the entire universe, predicts that the universe might have bounced rather than starting from an absolute singularity at the Big Bang. The bounce would leave imprints in the large-scale structure, potentially explaining the multipole anomalies. The bounce idea says the universe was contracting before the Big Bang, reached a minimum size, then rebounded and started expanding. During the contraction phase, quantum effects became important, preventing the universe from collapsing to zero size. The rebound launched the expansion we observe today. If this happened, the quantum state during the bounce would correlate large-scale modes in ways that standard inflation does not predict. The quadrupole suppression and the peculiar alignments could be echoes of the pre-bounce universe. This is speculative, not confirmed, but it shows how anomalies drive new theories. When observations do not match predictions, physicists develop new models that might explain the mismatch. Sometimes, the anomalies fade with better data. Sometimes they lead to revolutionary insights. The multipole anomalies remain puzzling more than 2 decades after their discovery. A fundamental frequency in the universe's temperature is far weaker than physics predicts. Imagine listening to an orchestra where all the instruments play beautifully except the bass section, which is barely audible. You would wonder what happened to the bass. Did the instruments break? Is something absorbing those frequencies? The cosmic microwave background faces this exact puzzle. The quadrupole represents temperature variations on the largest angular scales we can measure. It should be strong because inflation generates fluctuations at all scales with similar power. The models predict a certain amplitude for the quadrupole based on how smaller scale fluctuations behave. But when we measure it, the quadrupole comes in significantly weaker. This discrepancy has survived decades of scrutiny. Multiple missions found it, confirmed it, verified it with even better precision. The quadrupole is genuinely weak, about 30% below predictions. Why this matters beyond just one anomalous measurement. The quadrupole corresponds to the largest observable structures in the universe. If it is weak, that means the universe has less variation on the largest scales than expected. This could be telling us something profound about how inflation ended, or about the geometry of space beyond what we can observe. One possibility is that inflation did not last quite long enough to generate strong fluctuations at the very largest scales. If inflation ended just a bit earlier than assumed, the modes that would become the quadrupole might not have fully developed. They would still exist, but would be suppressed compared to smaller scales. Another possibility involves cosmic topology. What if the universe wraps around on itself like the surface of a hypersphere? If the universe is finite rather than infinite, then the largest possible fluctuations are limited by the universe's total size. A weak quadrupole could indicate that we are seeing the edge of possibility, where the universe simply does not have room for larger variations. Think of waves in a bathtub versus waves in an ocean. The bathtub limits how long the waves can be. The ocean allows much longer wavelengths. If the universe is more like a bathtub than an ocean, the longest wavelength fluctuations would be suppressed. Some researchers have explored whether we are living in a closed universe with a radius only slightly larger than our observable region. This would naturally explain the weak quadrupole, but other observations suggest the universe is flat, not closed, making this explanation problematic. The weak quadrupole might also connect to the Hubble tension and dark energy mysteries. If something unusual happened in cosmic history that affected expansion, it could also affect how large-scale fluctuations evolved. Maybe early dark energy or time variations in the expansion rate left an imprint on the quadrupole. No explanation has gained consensus yet. The weak quadrupole remains one of several small puzzles in the cosmic microwave background that do not quite fit the standard model. Scientists continue searching for explanations, but the answer remains elusive. The alignment problem is even stranger because it points toward Earth specifically. The octopole and quadrupole both show preferential alignment with the ecliptic plane, the plane in which Earth orbits the Sunday. This is deeply unsettling because the cosmic microwave background formed when the universe was 380,000 years old, billions of years before our solar system existed. There should be absolutely no relationship between structures in the ancient universe and the orientation of our local planetary system. It would be like finding your address written in rocks that formed before life existed on Earth. The coincidence is too specific to ignore, yet too bizarre to easily explain. Some scientists suggest foreground contamination. Maybe something in our solar system or galaxy is creating a false signal that looks like alignment. Dust in the plane of our solar system could emit microwaves that contaminate the cosmic signal. Researchers have attempted to model and subtract all known foregrounds, but the alignment persists even in the cleanest data. Others propose observer selection effects. Maybe we naturally find ourselves in a location where this alignment exists, because such locations are somehow more conducive to the formation of life. This ventures into controversial anthropic reasoning where the properties of the universe are explained by the fact that we exist to observe them. Most physicists find this unsatisfying because it does not explain the underlying physics, just why we happen to observe it. A more radical possibility is that the cosmological principle is wrong. This principle states the universe should look statistically the same in all directions and at all locations. It is a foundational assumption of modern cosmology, built into nearly every model. If the universe actually has preferred directions or large-scale structure that breaks symmetry, then the entire framework needs revision. Imagine discovering that your house is not oriented randomly, but aligns with magnetic field lines you were previously unaware of. The alignment itself does not make sense until you discover the hidden field. Maybe the universe has large-scale structure or fields beyond our current models, and the cosmic microwave background anomalies are the first hints. Loop quantum cosmology and bouncing universe models offer one framework for explaining these anomalies. If the universe underwent a quantum bounce instead of starting from a true singularity, the state before the bounce could correlate large-scale modes in unexpected ways. The quantum geometry during the bounce might impose preferred orientations that persist through the expansion. These models are mathematically sophisticated and make testable predictions, but they require accepting quantum effects on the scale of the entire universe, which pushes far beyond experimentally verified physics. We know quantum mechanics works at atomic scales. We know general relativity works at cosmic scales, but combining them remains one of physics' unsolved problems. The anomalies might also connect to cosmic topology again. If the universe has a non-trivial shape, like a three-dimensional torus or other complex manifold, then certain modes would be suppressed and others enhanced. The alignment could arise from how our observable patch sits within that larger topology. String theory and higher dimensional models sometimes predict that the extra dimensions could leave imprints on the cosmic microwave background. If extra dimensions exist and have particular geometries, they could affect how fluctuations propagate and create patterns that break perfect isotropy. All these explanations remain speculative because the anomalies, while real, are not strong enough to definitively rule out the standard model. They sit in an uncomfortable zone where they are too significant to ignore, but too weak to prove new physics. Future missions with higher sensitivity might either strengthen these signals to the point where they demand explanation, or show that they were statistical flukes that disappear with better data. For now, the axis of evil and the weak quadrupole stand as reminders that the universe still holds mysteries, even in its most carefully studied signals. The cosmic microwave background revealed the universe's baby picture, but that picture contains details we do not yet fully understand. Dark matter makes up 27% of the universe, but we have never detected a single particle of it. Every star, planet, nebula, and galaxy we observe consists of ordinary matter, the atoms described by the periodic table. Protons, neutrons, electrons, and the particles that compose them account for all visible structure in the cosmos. Yet this ordinary matter represents less than 5% of the universe's total content. The rest is invisible. 27% is dark matter, matter that does not emit, absorb, or reflect light. It interacts with ordinary matter only through gravity. We know it exists because we see its gravitational effects everywhere we look. Galaxies rotate too fast. The stars on the outer edges of spiral galaxies orbit the galactic center at speeds that should fling them into intergalactic space if only visible matter were present. The gravity from stars, gas, and dust is insufficient to hold these galaxies together. Yet galaxies do not fly apart. Something invisible provides additional gravity, binding galaxies more tightly than visible matter alone could manage. Galaxy clusters show the same problem. The galaxies within clusters move so rapidly that the cluster's gravity, calculated from visible matter, cannot contain them. Clusters should evaporate as galaxies escape, but they remain stable. Dark matter provides the additional mass required. Gravitational lensing offers even more direct evidence. When light from distant galaxies passes near massive objects, the gravity bends the light's path, distorting the background galaxies into arcs and rings. By measuring these distortions, astronomers map the distribution of mass, including dark matter. These maps show vast halos of dark matter surrounding galaxies and filling the spaces between them. The cosmic microwave background also requires dark matter. The pattern of hot and cold spots depends on how matter and radiation interacted in the early universe. Simulations show that getting the observed pattern requires far more matter than we see in stars and gas. Dark matter, which does not interact with light, fits the observations perfectly. Despite overwhelming indirect evidence, no one has ever detected a dark matter particle directly. This is one of modern physics' most frustrating mysteries. We know dark matter exists. We know approximately how much exists and how it is distributed. We know it must be composed of particles, but we do not know what those particles are. The leading candidate for decades has been WIMPs, weakly interacting massive particles. These hypothetical particles would have mass comparable to heavy atoms, but interact with ordinary matter only through gravity and the weak nuclear force. The weak force is incredibly feeble, operating only at subatomic distances, so WIMPs would pass through normal matter almost as if it were not there. Experiments have searched for WIMPs for more than 30 years. Detectors deep underground shield cosmic rays while waiting for a WIMP to occasionally collide with an atomic nucleus. These collisions should produce tiny flashes of light or heat that can be measured. Despite exquisite sensitivity, no confirmed WIMP detection has occurred. The lack of detection has pushed physicists to consider alternatives. Actions are much lighter hypothetical particles originally proposed to solve a different problem in particle physics. If they exist in sufficient numbers, they could account for dark matter. Axion detectors use different techniques than WIMP detectors, searching for signals produced when axions interact with strong magnetic fields. Sterile neutrinos represent another possibility. These are hypothetical particles similar to the neutrinos we already know exist, but even more elusive. They would interact with matter only through gravity, making them extraordinarily difficult to detect directly. Some physicists propose that dark matter is not particles at all, but rather a modification to the laws of gravity itself. Modified Newtonian dynamics, MOND, suggests that gravity behaves differently at very low accelerations than Newton's or Einstein's theories predict. This would eliminate the need for dark matter because the gravitational effects attributed to invisible mass would instead result from altered gravity laws. MOND works well for explaining galaxy rotation curves, but it struggles with galaxy clusters and the cosmic microwave background. It also lacks a relativistic version that properly incorporates time dilation and other effects Einstein discovered. Most physicists favored dark matter particles over modified gravity, but the complete absence of direct detection keeps alternatives alive. Recently, astronomers discovered galaxies that appear to lack dark matter entirely. If dark matter particles exist, why would some galaxies have none? This is puzzling for particle dark matter theories, but also challenges MOND because those theories predict galaxy dynamics should always differ from standard gravity. Galaxies without dark matter behave exactly as standard gravity predicts when only ordinary matter is present. These anomalous galaxies might have lost their dark matter through gravitational interactions with neighboring galaxies, or they might have formed in unusual environments where dark matter was absent, or they might be revealing something about dark matter physics we do not yet understand. The observations are recent and still being debated. The nature of dark matter remains unknown. It is a placeholder name for something we observe gravitationally, but cannot otherwise detect. Whatever dark matter consists of, it is one of the universe's dominant components, shaping the formation of every galaxy and influencing the cosmos's overall geometry. Finding dark matter particles would revolutionize physics. It would confirm that a whole category of matter exists beyond the standard model, opening new domains of research. Alternatively, if dark matter detection continues failing, physicists might eventually accept that gravity itself requires modification, forcing a rewrite of general relativity. Either outcome transforms our understanding. For now, dark matter remains one of the universe's greatest unsolved puzzles, hiding in plain sight throughout the cosmos. The universe might be even more mysterious than dark energy suggests, because dark energy itself might not exist. Two of the biggest mysteries in cosmology might actually be the same mystery viewed from different angles. The Hubble tension describes the mismatch between expansion rate measurements. Dark energy describes the mysterious force accelerating expansion. What if solving one solves both? Several recent theoretical proposals attempt exactly this. If dark energy varies with time or location, it could produce different expansion rates in different cosmic epochs, potentially explaining why early universe and late universe measurements disagree. If dark energy is actually misidentified time dilation effects from the lumpy universe, as the timescape model proposes, then both the acceleration and the tension are explained by the same new understanding. Think of two symptoms that seem unrelated. You have a headache and blurred vision. Doctors might treat them as separate problems, prescribing pain medication and glasses. But if both symptoms result from a single underlying condition, treating them separately misses the true cause. Only addressing the root issue resolves both. Cosmology might be facing a similar situation. The Hubble tension and dark energy could be symptoms of incomplete physics rather than separate phenomena. The Standard Model treats them as independent problems. The Hubble tension is a measurement puzzle. Dark energy is an acceleration puzzle. But both involve the expansion rate, and both emerged from increasingly precise observations over the past 25 years. Timescape cosmology unifies them by removing dark energy and explaining expansion through the universe's inhomogeneous structure. The tension dissolves because different measurements probe different aspects of the lumpy cosmos. Early universe measurements capture average expansion. Late universe measurements capture local expansion through overdense regions where we live. They disagree because they are measuring different things. Evolving dark energy models also unify the problems, but retain dark energy as a real component. If dark energy strengthened over cosmic history, early measurements would see a universe expanding slower than late measurements predict, matching the observations. The tension arises because we assumed dark energy was constant when it actually changed. Early dark energy models add complexity by introducing a second dark energy phase in cosmic history. This solves the tension by modifying the early universe's expansion in specific ways, allowing predictions to match local measurements. It also explains anomalies like the unexpected abundance of early galaxies observed by James Webb. Each approach attempts to resolve multiple puzzles simultaneously, a sign that the ideas might be on the right track. In physics, theories that explain more phenomena with fewer assumptions are generally preferred. If dark energy variations or timescape effects explain both the Hubble tension and apparent acceleration, that is more elegant than treating them as coincidentally occurring in the same era. But testing these unified explanations requires data that can distinguish between them. We need measurements precise enough to tell whether dark energy is constant, evolving, or illusory. We need maps of cosmic structure detailed enough to test whether lumpiness matters as much as timescape proposes. Those measurements are coming. Satellites launched recently and telescopes coming online in the next few years will provide the data needed. By the early 2030s, cosmology should have answers. Either the Standard Model will be confirmed with higher precision, revealing that the Hubble tension resulted from subtle systematic errors, or new physics will be required. The next decade represents a crucial period for cosmology. Technologies have reached the point where we can definitively test foundational assumptions. The universe is about to reveal whether it is stranger than we thought or stranger than we imagined possible. Gravitational waves from the Big Bang itself could prove inflation happened. When inflation exponentially expanded space, it should have produced ripples in space-time called gravitational waves. These primordial gravitational waves would still be propagating through the universe today, stretched to enormous wavelengths by cosmic expansion. Unlike gravitational waves from colliding black holes, which we have detected with instruments on Earth, Primordial gravitational waves are far weaker and have much longer wavelengths. They cannot be detected directly with current technology, but they left an imprint on the cosmic microwave background that can be measured. When gravitational waves pass through space, they create a specific pattern of polarization in light. The cosmic microwave background photons should show this polarization pattern if primordial gravitational waves existed. Scientists call this pattern B-mode polarization, distinguishing it from other polarization patterns produced by density fluctuations. Detecting B-mode polarization from inflation would confirm that inflation occurred and provide detailed information about how it happened. The strength of the signal depends on the energy scale of inflation. Higher energy inflation produces stronger gravitational waves. Measuring the signal tells us how energetic the inflaton field was. In 2014, a telescope at the South Pole announced detection of B-mode polarization. The scientific community erupted with excitement. Headlines proclaimed that inflation had been proven. But within months, the claim collapsed. Dust in our galaxy also produces B-mode polarization, and careful analysis showed the signal was mostly or entirely from dust, not from primordial gravitational waves. That false alarm illustrated how difficult this measurement is. The primordial signal is incredibly faint. Foreground sources like galactic dust emit much stronger signals. Separating the two requires understanding the foreground in exquisite detail. Multiple experiments continue searching. Detectors in Antarctica, Chile, and soon on spacecraft are mapping the cosmic microwave background's polarization with increasing precision. If primordial gravitational waves are detected, it would be one of the most important discoveries in physics. It would confirm inflation directly rather than through indirect evidence. It would tell us the energy scale at which inflation occurred, providing a window into physics at energies far beyond what particle accelerators can reach. The energy scale of inflation might have been close to the Planck scale, where quantum gravity effects become important. If so, primordial gravitational waves connect cosmology to one of physics' deepest unsolved problems: how to unify quantum mechanics and general relativity. Observing the universe's first moments might reveal clues about quantum gravity. But if primordial gravitational waves are not detected despite increasingly sensitive searches, that tells us something different. It means inflation, if it happened, was relatively low energy. Some inflation models predict detectable signals, while others predict signals too weak to ever observe. Ruling out the high-energy models would narrow the possibilities. The search continues. Each new experiment pushes sensitivity deeper, mapping fainter signals and removing foreground contamination more carefully. Within the next decade, experiments should either detect primordial B-modes or conclusively show they are weaker than current detection limits. This measurement has been called the Holy Grail of cosmology. Finding it would confirm ideas about the universe's first fraction of a second and connect cosmic observations to fundamental physics in unprecedented ways. Not finding it despite exhaustive searches would force physicists to reconsider which inflation models are viable. Either outcome advances understanding. The universe will tell us about its earliest moments whether the signal is there or not. We just need instruments sensitive enough to listen. The earliest galaxies appeared impossibly fast, challenging our understanding of cosmic evolution. The James Webb Space Telescope was designed to observe the first stars and galaxies, and it has succeeded beyond expectations. But what Webb found was not what theorists predicted. Galaxies appeared earlier, grew larger faster, and became more structured more quickly than simulations suggested. Standard models predict that after the Big Bang, the universe was filled with hydrogen and helium gas. Gravity slowly pulled this gas into clumps. The clumps collapsed to form the first stars a few 100 million years after the Big Bang. These stars lived, died, and enriched space with heavier elements. Successive generations of stars formed, eventually assembling into galaxies. This process should have taken time. Early galaxies should have been small, irregular, and relatively faint. Large spiral galaxies with organized structure should have emerged only after billions of years of evolution as smaller galaxies merged and gas settled into rotating disks. Webb sees something different. Galaxies observed at cosmic ages of 500 to 700 million years are surprisingly bright, large, and structured. Some show spiral arms. Some contain massive black holes. Some have already produced substantial amounts of heavy elements. These observations suggest galaxy formation happened faster than standard models allow. One galaxy, observed by Webb, existing only 330 million years after the Big Bang, has a mass comparable to the Milky Way. The Milky Way took over 13 billion years to reach its current mass. How did a galaxy grow so large so quickly? Several explanations are being explored. Maybe the first stars were far more massive than current models assume. More massive stars produce more heavy elements and more energetic feedback, potentially accelerating galaxy growth. But we do not know why early stars would differ from later ones. Maybe dark matter clumped more efficiently in the early universe than simulations predict. If dark matter formed denser halos faster, galaxies could have assembled more rapidly within those halos. But this requires adjusting dark matter properties in ways not supported by other observations. Early dark energy offers another explanation. If a burst of dark energy occurred in the first few 100,000 years, it would affect how density fluctuations evolved. Enhanced fluctuations could seed more rapid galaxy formation, creating larger galaxies earlier. Some researchers suggest that our distance measurements might be slightly wrong. If the galaxies are closer than we think, they would be intrinsically fainter and less massive, resolving the conflict. But Webb's measurements are precise, and multiple independent methods confirm the distances. Another possibility is that the galaxies Webb observes are rare flukes, statistical outliers that happen to form in unusually dense regions. If we observe a large enough volume, we should occasionally find galaxies that formed earlier or faster than average. But Webb keeps finding them, suggesting they might not be that rare. The observations are forcing theorists to reconsider assumptions about the early universe. Maybe structure formed from the bottom up as models predict, but the process was faster than calculations suggested. Maybe additional physics not included in standard models affected early cosmic evolution. This is how science progresses. Observations challenge theories. Theories adapt or get replaced. Each cycle refines understanding. Webb's discoveries do not overturn cosmology, but they reveal that our models of early galaxy formation are incomplete. Something about the first billion years is not captured by current simulations. Future observations will help. Webb continues surveying the early universe, finding more galaxies and measuring their properties in greater detail. Ground-based telescopes are confirming Webb's findings and providing complementary data. Within a few years, astronomers will have a statistical sample of early galaxies large enough to distinguish between explanations. If early galaxies genuinely formed faster than expected, that is not a crisis for cosmology. It is an opportunity to learn something new about how matter assembled in the universe's first billion years. The surprise is a gift, pointing toward physics we have not yet incorporated into our models. Black holes in newborn galaxies should not exist, yet Webb found them. Among the most startling discoveries from the James Webb Space Telescope are supermassive black holes in galaxies less than 1 billion years old. These black holes contain millions to billions of solar masses, sitting at the centers of galaxies that barely had time to form. Black holes grow by accreting matter. A stellar mass black hole, formed from a collapsed star, weighs tens of solar masses. To reach 1 million or billion solar masses, it must consume enormous amounts of gas and stars. This process has limits. When matter falls into a black hole, friction heats the gas to millions of degrees. The hot gas emits intense radiation that pushes surrounding matter away. This radiation pressure limits how fast the black hole can grow. The maximum growth rate is called the Eddington limit. A black hole growing at the Eddington limit continuously doubles its mass every few tens of millions of years. Starting from a stellar mass black hole, Reaching 1 billion solar masses requires hundreds of millions of years of continuous Eddington-limited growth. But some of the black holes Webb detected existed only a few 100 million years after the Big Bang. There was not enough time for them to grow from stellar seeds, even at maximum possible rates. This is called the supermassive black hole timing problem. Several solutions are being considered. Maybe black holes did not form from stars. If primordial black holes formed directly from density fluctuations in the extremely early universe, they could start with masses of thousands or even millions of solar masses. This head start would give them enough time to reach supermassive scales by the era Webb observes. Primordial black holes remain hypothetical. They would form from regions that were slightly denser than average, collapsing under their own gravity before stars existed. Simulations show this is possible under certain conditions, but we have no direct evidence primordial black holes exist. Another idea involves direct collapse black holes. Under special conditions in the early universe, massive gas clouds might collapse directly into black holes without forming stars first. If a cloud with 10,000 to 1,000,000 solar masses collapsed, it would immediately create a black hole of that mass. This seed could then grow to supermassive scales within the time available. Direct collapse requires suppressing normal star formation. Typically, collapsing gas fragments into stars before accumulating enough mass. But in environments flooded with ultraviolet radiation or lacking heavy elements, fragmentation might be suppressed. The entire cloud would collapse as one object, forming a massive black hole directly. Both scenarios remain speculative because we cannot observe them directly. The early universe is too distant and too obscured. We see the end results, supermassive black holes, but not how they formed. Simulations can test whether these mechanisms work in principle, but confirmation requires observational evidence we do not yet have. A radical alternative suggests black holes grow faster than the Eddington limit allows. If black holes accrete matter super Eddington for extended periods, they could reach supermassive scales quickly. Some theoretical models allow this under special conditions, but it requires rethinking standard accretion physics. Another possibility is that black holes merge frequently in the early universe. If galaxies collided and merged often, their central black holes would merge too, building up mass rapidly. But this still requires the initial black holes to be fairly massive, and galaxies in the early universe were small, making frequent mergers less effective. The discovery of these early supermassive black holes is reshaping theories of how galaxies and black holes co-evolve. For years, astronomers have known that supermassive black holes and their host galaxies grow together. The black hole mass correlates tightly with the galaxy's properties, but we did not know which forms first or how they influence each other. Webb's observations suggest black holes might form very early, possibly even before their host galaxies fully assemble. If true, black holes might play a more active role in galaxy formation than previously thought, seeding galaxies rather than being consequences of galaxy formation. This is frontier research. The observations are recent, and interpretations remain uncertain. Future observations will measure more early black holes, determine their masses and growth rates more precisely, and reveal how common they are. Combined with improved simulations, this will narrow the explanations. What is clear is that the early universe was more active and complex than models anticipated. Black holes formed fast. Galaxies formed fast. The first billion years of cosmic history witnessed rapid evolution that current theories do not fully explain. Something about the conditions or physics in that era enabled faster structure formation than later epochs experienced. The cosmic distance ladder has rungs that do not match, and the entire structure is wobbling. Astronomers measure distances to faraway objects using a series of techniques stacked on each other, forming a ladder. Each rung depends on the previous one. Errors at any level propagate upward, affecting all subsequent measurements. The ladder begins with geometric methods. Measure the distance to nearby stars using parallax, the apparent shift in position as Earth orbits the Sunday. This is direct and reliable. These nearby stars serve as calibrators for the next rung. The next rung uses standard candles, objects with known intrinsic brightness. If you know how bright something actually is and measure how bright it appears, you can calculate the distance. Cepheid variable stars serve as standard candles. They pulsate with periods that correlate tightly with their luminosities. Measure the period, determine the luminosity, compare to apparent brightness, and calculate distance. Cepheids can be observed in nearby galaxies using powerful telescopes. By measuring distances to these galaxies and observing their recession velocities, astronomers determine the local expansion rate. This yields the local Hubble constant. The problem is calibrating the Cepheid luminosities. This requires knowing the distance to Cepheids in our own galaxy, which depends on parallax measurements and other nearby distance indicators. Systematic errors in these calibrations shift all subsequent distances. Type Ia supernovae form the next rung. These exploding stars reach consistent peak brightness, making them visible across vast distances. By observing supernovae in galaxies with known distances from Cepheids, astronomers calibrate the supernovae brightness. Then supernovae in much more distant galaxies provide expansion rate measurements deep into cosmic history. Each transition introduces uncertainties. Maybe Cepheids in distant galaxies differ subtly from nearby Cepheids due to environmental differences. Maybe type Ia supernovae are not as standard as assumed, varying in ways we do not fully understand. Recent work discovered that type Ia supernovae appear slightly different depending on their host galaxy's properties. Supernovae in massive galaxies are not identical to supernovae in smaller galaxies. This variation was not fully accounted for in previous analyses. Correcting for it shifts distance measurements and affects the derived Hubble constant. The distance ladder also relies on assumptions about dust. Interstellar dust dims starlight and shifts colors toward red. Astronomers correct for this, but the corrections depend on assumptions about dust properties. If dust behaves differently in distant galaxies or early cosmic epochs, the corrections are wrong and distances are miscalculated. Another source of uncertainty comes from gravitational lensing. The gravitational field of foreground galaxies can slightly magnify background objects, making them appear brighter and thus closer than they are. This effect is usually weak, but for precision cosmology, it matters. Researchers constantly refine the distance ladder, improving calibrations and reducing uncertainties. The Hubble Space Telescope spent years observing Cepheids in dozens of galaxies, providing the best calibrations to date. James Webb is now observing Cepheids with even higher precision in galaxies Hubble could barely resolve. Early results from Webb confirm Hubble's measurements. The distance ladder is robust. The local Hubble constant really is 73, not an artifact of errors. This makes the tension with Planck's measurement of 67 even more concerning. Both sides have checked and rechecked. Both are correct within their methods, yet they disagree. This disagreement might point toward new physics rather than measurement problems. If the expansion rate genuinely differs between the early universe Planck observes and the local universe distance ladder probes, something must have changed during cosmic evolution. Dark energy evolution, time-varying constants, or unaccounted structure could explain this. Alternatively, something subtle about how we connect different cosmic epochs might be wrong. The cosmological model takes the early universe conditions Planck measures, evolves them forward using known physics, and predicts what the local universe should look like. The prediction does not match observation. Either the initial conditions are slightly off, the evolution is not what we think, or local conditions differ from the model's assumptions. Resolving this requires independent distance measurements that do not rely on the traditional ladder. Gravitational waves from colliding neutron stars provide one such method. The gravitational wave signal encodes the distance to the source. If the collision also produces light, astronomers can measure the source's recession velocity from its spectrum. Distance plus velocity yields the Hubble constant without needing Cepheids or supernovae. So far, Only one such event has been observed with sufficient precision. That single measurement favored the lower value around 70 between the two camps, but closer to Planck. But one event is not enough to draw strong conclusions. As gravitational wave detectors improve, dozens or hundreds of these events will be observed, providing an independent check on the Hubble constant. Time delays in gravitationally lensed quasars offer another independent method. When a foreground galaxy lenses a background quasar into multiple images, light from each image travels a different path length. The time delay between images depends on the geometry, which depends on distances and the Hubble constant. Careful modeling yields a Hubble constant measurement. This method has been improving rapidly. Recent results yield values around 73, agreeing with the distance ladder and disagreeing with Planck. But the method requires modeling the mass distribution of the lensing galaxy precisely, and uncertainties in that modeling affect the result. Multiple methods now point toward a higher local Hubble constant than Planck predicts, strengthening the case that the tension is real, not methodological. The universe genuinely expands faster locally than early universe physics predicts. Something is missing from our models. Within a few years, independent measurements will either confirm or resolve the tension. If they all converge on the same value, whichever side is wrong will know where to look for errors. If they continue disagreeing with each other and with Planck, the crisis deepens and demands new physics. The fate of the universe depends on numbers we are still struggling to measure precisely. Will the cosmos expand forever, eventually tearing apart every structure until nothing remains but isolated particles in infinite darkness? Or will expansion reverse, collapsing everything back into a singular point of infinite density? These are not philosophical questions. They are physical predictions that depend on measurable quantities. The universe's fate hinges on the balance between its expansion rate, matter density, and dark energy properties. If dark energy remains constant and positive, expansion accelerates forever. Galaxies recede faster and faster. Eventually, galaxies outside our local group move away faster than light, disappearing beyond the cosmic horizon. Trillions of years from now, the night sky will go dark as distant galaxies fade from view. Stars will exhaust their fuel. New stars will stop forming as gas disperses. White dwarfs will cool. Neutron stars will slow. Black holes will slowly evaporate through Hawking radiation. Over unimaginable timescales, even protons might decay, leaving nothing but photons and neutrinos spreading infinitely apart. This heat death scenario is cold, dark, and eternal. It is currently the favored outcome based on observations, but it depends on dark energy behaving as a cosmological constant. If dark energy weakens over time, the outcome changes. Expansion could slow, stop, then reverse. The universe would enter a contraction phase, eventually collapsing in a big crunch. This future is fiery rather than cold. Matter compresses, heats, and merges. Structure breaks down as everything converges. A third possibility involves dark energy strengthening. If dark energy's density increases as the universe expands, acceleration intensifies. This leads to a big rip. Expansion becomes so vigorous that it overcomes all forces holding structures together. First, galaxy clusters disperse. Then galaxies dissolve as stars are pulled apart. Then solar systems break up. Eventually, even atoms are torn apart, as space itself stretches faster than forces can hold matter together. The Big Rip is violent, occurring in finite time rather than asymptotically. Current observations suggest none of these extreme scenarios is imminent. Dark energy appears consistent with a cosmological constant, leading to heat death trillions of years hence, but uncertainties remain. Small changes in dark energy's properties shift the outcome dramatically. Another possibility that has gained attention recently involves vacuum decay. Quantum field theory suggests the vacuum of space might not be in its lowest possible energy state. If a lower state exists, the vacuum could tunnel to that state, creating a bubble of true vacuum that expands at light speed, destroying everything in its path. The transition releases enormous energy, but that energy remains inside the bubble. From outside, the bubble's wall approaches silently and invisibly at light speed. You would never see it coming. The moment it arrives, the laws of physics change inside the bubble, potentially making matter unstable. This is speculative. We do not know whether a lower vacuum state exists. If it does, we do not know how long the current state typically persists before decaying. It could be vastly longer than the current age of the universe, making vacuum decay irrelevant. Or it could happen tomorrow. The probabilities are unconstrained because we lack a complete theory of the vacuum. Some physicists find vacuum decay unlikely because the universe has existed for nearly 14 billion years without such an event occurring. If the probability per year were significant, it likely would have happened already. But this anthropic argument only weakly constrains the risk. The universe's fate remains uncertain because dark energy remains mysterious. Learning what dark energy truly is will reveal what awaits all matter and energy across infinite time. That answer is perhaps cosmology's deepest question, and it might be answered within decades. We are living in a special time cosmologically, able to see the universe's past before dark energy obscured it. If humans had evolved 100 billion years from now, cosmology would be impossible. All galaxies, except those in our local group, will have receded beyond the cosmic horizon, carried away by accelerating expansion. The cosmic microwave background will have redshifted into undetectable radio wavelengths, its information lost. Future civilizations would observe a single isolated galaxy surrounded by darkness. They could study stars, planets, and local phenomena, but they would have no evidence the universe extends beyond their galaxy. They would not know about the Big Bang. They would not know about cosmic expansion. They would have no way to determine the universe's age or composition. From their perspective, the universe would appear eternal, static, and small. Everything we have learned about cosmology would be forever beyond their reach. The evidence would have literally moved away faster than light can carry it back. This realization emphasizes how fortunate we are to live in an era where cosmology is possible. The cosmic microwave background is still visible. Distant galaxies are still observable. The expansion rate is measurable. We can reconstruct cosmic history from the Big Bang to the present. But the window is closing, not on human timescales, but on cosmic ones. Within trillions of years, the evidence of cosmic origins will disappear. The universe will have expanded so much that any observers will find themselves alone in darkness with no way to learn the truth. This raises profound questions about the nature of knowledge and the role of observers in the cosmos. Are we lucky to exist in an observable era? Or is our existence precisely when observers would naturally arise, because this is when complex structures can form? The universe might be full of eras where life cannot exist, and epochs where observers could exist, but would lack the evidence to understand cosmology. We happen to be living in the narrow window where both conditions are met. That is either extraordinary coincidence or a selection effect. We can only observe from times and places where observers exist, so of course we find ourselves in an observable era. This ties to ongoing debates in cosmology about the anthropic principle and whether the universe's properties require special explanation. Some features of the universe appear fine-tuned for life. If constants of nature were slightly different, atoms, stars, or galaxies could not exist. Does this fine-tuning demand explanation, or is it simply a selection effect? If countless universes exist with different properties, we naturally find ourselves in one, compatible with our existence. Universes where stars cannot form would have no observers to wonder why. This is the multiverse hypothesis, controversial because other universes are, by definition, unobservable. Critics argue that invoking unobservable universes to explain our universe's properties is not scientific. Proponents counter that it is a natural consequence of inflation and string theory, both of which predict multiple regions of space with different physical laws. Regardless, Our privileged position in cosmic history is temporary. We can see evidence of the universe's origins now, but that evidence is gradually fading. Every observation we make today teaches something that future civilizations might never learn. In that sense, cosmology has urgency. We are racing against cosmic expansion to extract as much knowledge as possible before the clues disappear beyond the horizon forever. The measurements we make today will echo across time, potentially being the only records of what the universe was like in its observable phase. That gives contemporary cosmology a unique significance. We are documenting the cosmos not just for ourselves, but for all future observers who will inherit a darker, emptier universe, stripped of its revelatory past. Space is expanding, time is flowing unevenly, and our observations are entangled with the structure of reality itself. The universe's expansion has forced humanity to confront mysteries that challenge every assumption about existence. Nothing is as simple as it first appeared. The rate of expansion disagrees with itself. Ancient light tells one story. Nearby galaxies tell another. Both measurements are correct, yet they are incompatible. Either our instruments deceive us in ways we cannot detect, or the universe operates by rules we have not yet grasped. Dark energy might be real, an invisible force pushing space apart with increasing vigor, or it might be an illusion created by comparing clocks that ran at different rates across cosmic voids and galaxy clusters. Time itself might flow unevenly through the cosmos, warping our perceptions of distance and acceleration. The first fraction of a second might have witnessed inflation, an exponential surge that smoothed space, seeded galaxies, and set the stage for everything that followed. Or it might have been a quantum bounce, the universe rebounding from a previous contraction, carrying echoes of a reality that existed before our Big Bang. Galaxies formed too quickly. Black holes grew too massive. Structure assembled faster than simulations allow. The early universe was more dynamic, more surprising, more productive than theories predicted. Something about those first billion years remains beyond our current models. Dark matter surrounds every galaxy, binds every cluster, and shapes cosmic structure through its gravity. Yet, we have never detected a single particle. It could be WIMPs, axions, or primordial black holes. Or it could be evidence that gravity itself requires modification at cosmic scales. The cosmic microwave background shows patterns that should not exist. Temperature variations are too weak at large scales. Strange alignments point toward Earth's orbital plane for no conceivable reason. These anomalies might be statistical flukes, or they might be the first hints of new physics written into the universe's baby picture. Expansion might be accelerating, decelerating, or doing both at different times. Dark energy might be constant, evolving, or non-existent. The fate of all matter depends on which of these is true. Will everything end in cold isolation, fiery collapse, or violent tearing? The answer will come soon. Telescopes are mapping the cosmos with unprecedented precision. Satellites are measuring distances, expansion rates, and cosmic structure. Within a decade, cosmology will either confirm the standard model with ironclad certainty or reveal that reality operates by principles we have yet to discover. We are living in cosmology's golden age, able to observe the universe's past before dark energy obscures it forever. Future civilizations will inherit a darker sky, emptier space, and fewer clues about cosmic origins. The evidence is fading, redshifting into invisibility as expansion carries it beyond the horizon. Every measurement matters. Every observation adds a piece to the puzzle. And every puzzle piece reveals that the universe is stranger, richer, and more mysterious than anyone imagined. Space tears itself apart faster than it should. Time flows unevenly across cosmic voids. The numbers do not match, and something fundamental is broken in our understanding of reality itself.